Hello APC Mechanics students, in Unit 2 Newton's Laws of Motion, Class 3 Forces, Part 3. Then Section 1, the normal push, level surface. A box is placed on a horizontal level surface. As we can see that a box has been placed on a level surface. The forces acting on the block are the pull of gravity down, the normal push is up, exerted by the level surface on the box. These forces are balance forces along the vertical because we have no motion, so we can say that the normal push is equal to the pull of gravity. Now suppose we add two forces, the horizontal force F1 to the right and the horizontal force F2 to the left. Because these forces are horizontal forces, then the expression of the normal push will stay the same. Then whenever we have a box on a level surface and we have horizontal forces acting on the box, the expression of the normal push won't be affected and it's equal to the pull of gravity. Keep in mind that the normal push is a contact force and it would be affected based on the situation or the problem. Now we will add a pulling force F up. So we're pushing the box against the level surface. We will investigate how this will change the expression of the normal push. Along the vertical, we can say that the normal push, so the forces up is equal to the forces down, so the normal push plus capital F, the pulling force, is equal to the pull of gravity because they are balance forces. And if we're searching for the expression of Fn, then Fn would be given by Fg minus F. Then in this case the expression of the normal push changes from the pull of gravity into the pull of gravity minus F, and if you notice carefully, which means the normal push decreases whenever we apply a pulling force. And in this case, the representation of this factor is wrong, and it should be replaced by a smaller vector such that the normal push, the length of the normal push plus the pushing force F, should be equal to the pull of gravity. Forces pulling against the level surface decreases the value of the normal push. So whenever we have a pulling force, that would decrease the value of the normal push. How about adding a pressing force F down? So now we are adding a force which is helping the pull of gravity. Now in this case, vertical forces, we know that they're gonna affect the expression of the normal push. So along the vertical, what do we have? We have the normal push which is up. It's being balanced by the pushing force and the pull of gravity, or the pressing force. And if we're searching for the expression of Fn, then Fn is given by Fg plus F, which means that the expression of the normal push changes from being the pull of gravity to the pull of gravity plus the pressing force. And in this case, the representation of the normal push as a vector is wrong, because in this case the normal push is equal to the pull of gravity. It should be replaced by a vector which compensates for the pressing force, which means we should add these two forces, and we expect that the normal push will increase in magnitude. Pressing forces against the level surface increases the value of the normal push. Now taking it to a new level, we will add a pulling force F having both vertical and horizontal components upright. So now we have added a new force which is a pulling force making an angle theta with the horizontal, and we will see how this would affect the normal push. Components of vertical forces affect the expression of the normal push. Then along the vertical, now we know that this force can be decomposed solely along the horizontal and along the vertical. Since theta is the angle with the horizontal, then the horizontal component would be given by F cosine theta, but we know that the horizontal component does not affect the expression of the normal push. However, the vertical component, which is F sine theta, would affect the expression of the normal push. Because this is acting up, we would expect that this would help the normal push, and by that the value of the normal push will decrease. So along the vertical, we can say that Fn plus F sine theta is equal to the pull of gravity, and we're searching for the value of Fn. Then Fn in this case is given by the pull of gravity minus F sine theta, which means that the expression of the normal push changes from being the pull of gravity to the pull of gravity minus F sine theta, which is the vertical component of the pulling force. And in this case, the vector representation, this is wrong. Fn should be replaced by another Fn, which is smaller in magnitude, such that the length of this vector plus this vector is equal to the pull of gravity. Forces pulling against a level surface decreases the value of the normal push. Only vertical components of forces affect the expression of the normal push. Horizontal components do not affect the normal push. Now if we add a pressing force F having both vertical and horizontal components down right, like that, so in this case we are applying a pressing force, but the pressing force is not completely vertical, it's making an angle theta below the horizontal. Now we can decompose this force into horizontal and vertical component. The vertical component would be F sine theta. Components of vertical forces affect the expression of the normal push. Along the vertical, we have F sine theta. Then in this case, we can say that the normal push, which is up, is equal to Fg plus F sine theta, which is down. These are balanced forces because there is no motion along the vertical. And if we're searching for the expression of the normal push, indeed the normal push is Fg plus F sine theta, which means that the expression of the normal push changes from Fn, which is Fg, into Fg plus F sine theta. And in this case, the normal push, since it increases, it should be replaced by a larger, taller, longer vector, such that this length is equal to the pull of gravity plus F sine theta. Forces pressing against a level surface increase the value of the normal push. Alright, and we don't care about the horizontal component because they don't affect the expression of the normal push. Now let's do a recap or summary about how the normal push is being affected by other forces. First of all, for a level surface, the normal push is equal to the pull of gravity. Fn is Fg. This is idea number one. Idea number two, the normal push is a variable force. Its magnitude depends on the situation, so we should be very careful. We cannot directly claim that the normal push is equal to the pull of gravity. We need to pay attention if there is any pulling or pressing force. Adding a pressing force will increase the magnitude of the normal force, which means that if we add a force which is downward or having a vertical component downward, that would increase the value of the normal push. And adding a pulling force will decrease the magnitude of the normal force, so adding a pulling force completely upward or making an angle theta with the horizontal would decrease the value of the normal push, and you can understand that as if it's helping the normal push in order to equate gravity. Alright, example 1. A 2 kg block is initially at rest on a horizontal frictionless table. A force of 15 newtons is then exerted on the block at an angle 37 degrees to the horizontal as shown. Determine the magnitude of the force exerted on the block by the table. So about which force we're talking? We know that we're talking about the force exerted by the table on the block. We know that this is the table. So basically the table is preventing the block from falling down, and we can explain that at the level of the forces. So the table exerts a normal push on the block upward. So in this case we are interested in determining the normal push. Now the normal push basically would be equal to the pull of gravity if there are no vertical forces acting on the block. However, here we have a vertical force. What is the type of this force? This is a pressing force, which means that it will increase the value of the normal push. And here let me specify, so let me say this is capital F, which is 15 newtons, and let me specify the angle that this force F makes with the horizontal. So this is another horizontal and these two lines are parallel, then this is 37 degrees. Why? Because these two lines are horizontal, then they are parallel and they form the Z shape, then this angle is equal to this angle. And now we can say that along the vertical, what do we have? So basically, let me also here draw the pull of gravity, which is down, and the normal push, which is up. So what are the forces that are acting up? We have the normal push is up, and it's being balanced by the forces that are down. We have the pull of gravity, and we have the pressing force multiplied by the sine of the angle that the force makes with the horizontal, and that would be 37. We are interested in finding the value of the normal push, and this is the reason because they are balanced forces. So the normal push would be equal to the pull of gravity, which is given by mg, plus capital F sine 37. The mass is given by 2g is given by 10. The capital F is given by 15, and that would be sine 37. Now plugging that on the calculator, we would get a value of the normal push, which is given by 29.03 newtons. and if you compare carefully, the pull of gravity is given by 20 newtons. Due to the pressing force, the normal push would change from 20 newtons to 29.03 newtons. Now section 2, the normal push ramp, not a level surface. A box is placed on a rough ramp inclined by theta and remains at rest. Now in such type of problems, we would be interested in defining the x-axis to be along the ramp and the y-axis to be perpendicular to the ramp, and not to consider the horizontal and the vertical. What are the forces acting on the ramp? We have the pull of gravity, which is down. We have the normal push, which is perpendicular to the ramp, up left. We have the friction force, which is opposite to the tendency of motion upright. We suppose that due to the action of the gravity, the box would slide downward. For this reason, the friction would be up along the ramp, upright. Now, for the purpose of this section, friction will be removed, although it is present, but we won't represent it on the FBD, I suppose, or the vector diagram. We will investigate for the modified expression of the normal push. Remember that always and forever, the normal push is a variable force, and it's not always given by the pull of gravity. In case of a level surface with no vertical forces yet, yes, it is given by the pull of gravity. However, whenever we start adding vertical forces, the normal push, the expression of the normal push would change. Now forces are balanced along the y-axis. So here also pay attention that I'm mentioning the y-axis and not the vertical. Then what do we have? So before doing anything, let me decompose the pull of gravity along the y-axis. Now if this is the angle theta, then as we have explained previously, that would be the angle theta that Fg makes with the y-axis. Then the projection of Fg along the y-axis would be Fg cosine theta. Now in this case, we can say that the normal push is given by Fg cosine theta because they are balanced forces, and we are searching for the expression of Fn, which is basically given by Fg cosine theta. Then the normal push exerted by a ramp inclined by theta with or without friction and in motion or at rest, independent of anything, is given by Fg cosine theta. For simplicity, also we will remove the pull of gravity. So now we know that the normal push is given by Fg cosine theta. Now let's now add some pressing and pulling forces. If you apply a pressing force F against a ramp, it has both x and y components making an angle alpha with the y-axis. So in this case, because this is a pressing force against the ramp, we suppose that the normal push will increase in magnitude similar to the level surface. Components of forces along the y-axis affect the expression of the normal push. Then let me say along the y-axis. Now here we need to decompose this along the y and the x-axis. Since alpha is the angle between F and the y-axis, then the y component would be given by F cosine alpha. So we can say the forces that are down along the y given by F cosine alpha and Fg cosine theta would be balanced by the normal push. Then the normal push is given by Fg cosine theta plus F cosine alpha. Because they are balanced forces, there is no motion along the y-axis. We're not talking about the x-axis. So in this case, for a ramp, if we have a pressing force, the normal push would change from Fg cosine theta into Fg cosine theta plus F cosine alpha. And remember that alpha is the angle between the pressing force and the y-axis. And here, as you can notice that, okay, basically the value of the normal push increased from being Fg cosine theta into Fg cosine theta plus F cosine alpha. Then if we need to do the correct representation, the normal push, which is equal to Fg cosine theta, should be replaced by a larger vector to compensate for the additional term given by F cosine alpha. Forces pressing against the ramp increases the value of the normal push. Now if you're applying pulling force F against the ramp, it has both x and y components making an angle alpha with the y-axis. Now here in this case, this is a pulling force, as we can see here, which means this will help the normal push, which makes a decrease in value. Components of forces along the y-axis affect the expression of the normal push Fn. Along the y-axis, we will decompose F solely along the y and along the x. alpha is the angle between F and the y-axis, so its component along the y-axis is given by F cosine alpha. So in this case, the forces up along the y, which is given by Fn and F cosine alpha, would be balanced by Fg cosine theta, and we're searching for the expression of Fn. Now dragging this to the other side, then Fn would be given by Fg cosine theta minus F cosine alpha, and indeed the expression of the normal push changes from being Fg cosine theta to be modified Fg cosine theta minus F cosine alpha, and in this case we need to replace the normal push by a shorter vector because it has decreased in magnitude, and that would be the correct representation. Forces pulling against the ram decreases the value of the normal push. And now let's do a summary. For an inclined plane or ramp, the normal push is given by Fg cosine theta in the absence of any pressing or pulling force. The normal push, remember that it's a variable force, its magnitude depends on the situation. Adding a pressing force will increase the magnitude of the normal force. Adding a pulling force will decrease the magnitude of the normal force. And now let's do some exercises. An object weighing 300 newtons is suspended by means of two cords as shown above. Determine the tension in the horizontal cord. So here, how many cords do we have? Let me name them. This is cord 1, this is cord 2, and this is cord 3. Now the cords here that we're supposing they have the same tension along all points. So let me explain more. We need to determine the tension in the horizontal cord, the cord 2. So let's suppose this is the point A, and here we have the string 1. So at the point A, because the tension always points away, we have a tension T1 pulling down. At 2 we have a tension T2 pulling away from A to the left, and at 3 we have a tension pulling away from A, T3, like that. So let me say this is the horizontal. If this is 45, then that would be also 45 because this is a horizontal, this is a horizontal, and they have the Z shape. So that would be 45 degrees. Now what is the value of the tension T1? It is equal to 300 newtons, because notice that this object has a weight or a pull of gravity equal to 300 newtons, which means that the tension up is given by also 300 newtons. But I have mentioned something, that tension along the same rope or cord is the same, which means at this point, if the tension is 300 newtons, which also make the tension T1 at this point to be 300 newtons. So what we have is that basically T1 is equal to the pull of gravity, which is 300 newtons. So this is the first thing that we can say, that T1 is 300 newtons. Now we need to find the tension in the horizontal cord. So in order to do so, we need to balance the forces along the horizontal and along the vertical. Let me start with the vertical. Along the vertical, what do we have? We have the tension T1, which is down. It's being balanced by the vertical component of T3, which is up, so T3. And if 45 is the angle between T3 and the horizontal, then we're gonna multiply by sine 45. So as you can notice that along the vertical we don't have the expression of T2, which is the tension along the horizontal cord. So now we need to apply again along the horizontal. So what are the forces acting along the horizontal? We have T2, which is left, being balanced by the horizontal component of T3, which is right, and given by T3. Cosine 45, and we are interested in finding the value of T2. However, we don't know the value of T3. T3 can be determined from this equation, so let's determine T3 first. T3 is given by T1 divided by sine 45, and the value of T1 has been determined to be given by 300 divided by sine 45, and that would be in newtons. Now we can plug the expression of T3 here. That would be 300 divided by sine 45 multiplied by cosine 45, and you can check that these two are equal, and the value of T2 would be given by 300 newtons. Now exercise 2, a system in equilibrium consists of an object of weight W that hangs from 3 ropes as shown above. The tensions in the ropes are T1, T2 and T3. Determine in terms of W the expression of T2 and T3. It is exactly similar to what we have done previously. Let me consider this is the horizontal. If this is also the horizontal, then that would be parallel to this, and this is given by 60 degrees. Now T1 would be equal to W because the tension along the same cord or rope is always equal. Now we need to determine T2 and T3 in terms of W. So we need to apply it solely along the horizontal and along the vertical. Let me start by the vertical. Along the vertical, what do we have? So let me suppose this is the point A. We have T2 which is left, we have T3 which is upright, we have T1 which is down. So basically T1 would be balanced by, which is down, by T3 sine 60, because 60 is the angle with the horizontal. Then sine 60 would give us the vertical component. We are interested in determining T3. Then T3 would be given by T1 divided by sine 60. Now the value of T1 is given by W, sine 60 is given by radical 3 over 2. Now that would be 2 over radical 3 multiplied by W. We can rationalize by multiplying by radical 3, and that would be eventually 2 radical 3 divided by 3 multiplied by W. Then that would be the expression of T3. Now along the horizontal, we say that the tension T2 which is left would be equal to T3 cosine 60, and we are interested in determining the expression of T2. T3 is given by 2 radical 3 divided by 3 W multiplied by cosine 60, which is half. This 2 cancels with this 2, which makes T2 to be given by radical 3 divided by 3 W. And here remember that no need to place any unit because they are expressed in terms of another quantities. Now exercise 3, a sphere of mass m hangs from 2 strings that each make an angle 30 degrees with the horizontal as shown in the figure. What is the tension T in one of the strings? So let me say that the mass is given by 2 kg. So let me say this is the mass m. So what are the forces acting on the mass m? We have the tension T along the string which is upright, and we have the tension here which is also equal to T which is up left, and we have the pull of gravity. So along the vertical, we can say the pull of gravity which is down is being balanced by the vertical component of these 2 tensions. So if this is 30 degrees, let me draw here a horizontal, then that would be 30 degrees, and that would be 30 degrees. So the vertical component of the first tension force would be given by T sine 30, and the vertical component of the second tension force, which is also up, would be given by T sine 30. Now the pull of gravity is given by 2 multiplied by 10, and here we have T sine 30 is half plus T multiplied by half. Now half of T would give us T, so 20 would be equal to T, which means that T is equal to 20 newtons. Now exercise 4, which is an exit ticket for today's class. An object is at rest on a rough incline, so rough means that we have friction. At rest, which means no motion. As shown in the figure above, which of the following free body diagram best shows all of the forces acting on the object? We have the pull of gravity which is down. We have the normal push which is perpendicular to the plane. The tendency of motion due to the pull of gravity is down, so we expect that we should have friction up the ramp. So let's start eliminating. This is wrong because the normal push should be perpendicular to the plane. This is also wrong. This is wrong because the normal push is up. we're left with either A or B. We know that the pull of gravity should be down, so this is wrong, and the correct one would be A. Then that's it for me in this video, guys. See you soon in a new one.